In this video, I'm going to show you how to build a cost-effective 1 kW lab bench power supply. A DIY lab bench power supply is one of the most popular genres of project out there, with many resources to choose from. However, most follow a formulaic approach of shoving pre-made modules into a case and calling it a day. While there is nothing wrong with that, it gets repetitive after a while. I wanted a truly creative and engineered solution. Introducing the Forwarder 1 kW. The Forwarder 1 kW is a custom-designed module engineered as a cost-effective, simple, and reliable solution for your DIY builds. It delivers a maximum continuous output of 1 kW, with configurable ranges from 50 volts 20 amps up to 400 volts 2.5 amps. This makes the design highly adaptable whether you require high voltage or high current. For regulation, the Forwarder 1 kW implements dual constant voltage and constant current. This means that in addition to the voltage control loop, the current can be precisely limited. This is essential for tasks like electronic prototyping where you need overcurrent protection or safely charging various types of batteries with constant current mode. The Forwarder 1 kW features extensive interfaces for control and monitoring. The control port handles the power stage and fan, while a voltage reference interface sets the output voltage and current using a standard 2.5 volt analog signal. Simultaneously, an output sense interface provides analog feedback of the voltage and current for real-time monitoring. To keep things moving, here are the key features of the Forwarder 1 kW. With the features covered, let's get into the build process. To begin the build, I sourced the components to meet my design target of a 50 volt 20 amp output. The bill of materials is specifically adapted for this setup. If you want to explore a different configuration, you'll need to adjust the calculations and change certain component values, which I'll cover in a separate video. For now, let's focus on the heart of the build, the custom PCB, which was kindly provided by nextpcb. This project is sponsored by nextpcb, an industry-leading digital manufacturing platform for high-quality PCBs and turnkey assembly. If you want to build this project yourself and support my work, head down to the video description and click my affiliate link. Just go to the standard PCB quote page, upload the Gerber files from my GitHub page, and nextpcb's online quoting system will automatically detect all the correct design parameters. If you're looking for a quick PCB assembly, check out nextpcb's Ref0 PCBA prototype program. With the bare PCB ready, assembly begins by soldering the PWM generation circuit, which includes the resistors, capacitors, transistors, and the auxiliary power supply module. For the IC, you should use a socket to allow for easy replacement. For ease of assembly, solder the smaller components first before moving on to the larger components. Before we continue, the control circuit must be verified. First, use a multimeter to ensure the voltages are present on the power rails. Next, connect an oscilloscope, enable the power stage, and probe the PWM output pin. Adjust the onboard trimmer potentiometers to set the switching frequency to 64 kHz and the dead time to 10%. With the frequency and dead time tuned, we're ready for the next part. Before assembling the regulation circuit, the reference voltages for the voltage and current set points must be established. You should use multi-turn potentiometers to allow for precise output tuning. Wire them according to this configuration and verify a full 0 to 2.5 volt range at the wiper outputs. Once these references are confirmed, solder the remaining components for the regulation section. Before moving to the power stage, the feedback loop logic must be verified. Upon power up, the circuit should output maximum PWM. Injecting 5 volts into pin 2 for the current loop or pin 13 for the voltage loop should cause the PWM signal to drop completely. This behavior confirms that the regulation circuit is functioning correctly, meaning the board is ready for the power electronics. After confirming the control circuit is functional, we'll move on to the input rectifier and the power stage. To begin with, we need to prepare for the heatsink. For this build, I'm using a 10 by 45 by 200 mm aluminum heatsink. First, cut the heatsink to a length of 85 mm. Next, drill and tap the mounting holes to the heatsink. Finally, secure the heatsink to the board using nylon spacers and screw it firmly into place. With the heatsink in place, we'll continue with the input rectifier circuit. Start with the smaller components, the fuse holders, bleeder resistors, NTC inrush limiter, and the class Y capacitors. Move on to the medium-sized parts next, including the connector, relay, class X capacitors, common mode choke, film capacitors, and the bridge rectifier. Finally, solder in the large bulk electrolytic capacitors. For the power stage circuit, we need to finish the complementary components for the gate drive circuit. Once those are in, mount the MOSFETs to the heatsink with screws and thermal pads, then solder the leads of the MOSFETs. Next, we can proceed with the gate drive transformer. Wind 7 turns of 3 parallel wires on the T25 core, then solder it into place. To verify everything is working as intended, probe both gate-to-source voltages on the MOSFETs. You're looking for waveforms that are clean, square, and perfectly opposing without any overlap. Once those signals are confirmed, we're ready for the most critical part of the build, winding the main transformer. To create the main transformer, we'll need an ETD49 core and a 0.5mm enameled copper wire. We'll start with the first half of the primary winding. For this, you'll need 7 strands of wire. Prepare the ends by scraping away the enamel to expose the copper and tinning them with solder. Now, here's a neat trick for winding your own transformer. Apply heat shrink tubing to each bundle of wires. This not only looks much neater, but also improves safety by providing an extra layer of insulation where the primary and secondary might touch each other. After soldering one bundle to the transformer pins, we can begin winding the first half of the primary winding. To maximize winding efficiency, I have calculated that each layer should ideally hold 44 strands. The first half of the primary fits into 3 layers of 42 strands each. For the first layer, wind 6 turns of the bundle. Once finished, temporarily anchor it and apply a layer of transformer tape. Repeat this until you've completed 3 layers, then route the bundle back to the starting site and solder it to the corresponding pin. Before we wind the secondary, we need to add our first Faraday shield to improve EMI. Prepare a piece of copper foil cut to the correct dimensions. Solder a drain wire to the copper foil and apply the copper foil over the primary winding. Finally, apply 3 layers of transformer tape. With the first half of the primary done, it is time to wind the secondary. Split your wires into 6 bundle pairs, consisting of 5 and 4 strands each. Wind the first pair of bundles 5 turns up and then 5 turns down. Isolate the layer with tape and repeat the process for the remaining bundles. Once the secondary is complete, apply another 3 layers of tape. Next, install your second Faraday shield exactly like the first one. Apply a layer of tape over the second shield, then finish the transformer by winding the second half of the primary. Finally, assemble the transformer by fitting the ferrite cores and clamping them together with tape. If you're looking for a deeper dive into the techniques of winding ferrite core transformers, Diode Gone Wild has an excellent video on this subject. I highly recommend checking it out. Before installing the transformer, let's populate the output rectifier circuit first. Start by soldering the snubbers for the diodes, then mount the secondary heatsink before soldering the diodes onto the board. Finally, solder the main power transformer in place. The output inductor uses the same ETD49 core as the transformer. Wind 19 turns of 25 parallel strands of 0.5mm wire. The core needs an air gap to achieve the target inductance of 47 microhenry. To achieve this, I shimped the core with 1.9mm fiberglass plates. With the inductor ready, install the remaining output stage components including the loading and current sensing resistors and the output capacitors. Finally, solder the inductor into place. With all of the components in place, the board is finally finished. With the board populated, it is time for the initial power on. To ensure safety, we'll start by preparing a current-limited AC supply. You can use an incandescent bulb in series, or in my case, a DC to AC inverter. Either option will protect the circuit from potential catastrophic failure. Set both potentiometers about half turn from their minimum positions. First, perform a voltage test. Power up the setup, enable the power stage, and adjust the voltage potentiometer to verify the full 0 to 50 volts output. Next, disable the power stage and switch to the current test. Carefully short the output, enable the power stage again, and test the current up to 2 amps. If these checks pass, the power supply is fully functional and ready for the next part of the build. To achieve the functionality of a proper lab bench power supply, the board must be integrated with its supporting hardware. The assembly begins with the enclosure. I ordered a custom case based on 3mm acrylic plates with a transparent side panel to keep the internals visible. First, install the power supply board into the case using 5 M3 standoffs. Next, mount the voltage and current reference potentiometers to the front panel and connect them to the board. To monitor the output status along with real-time voltage and current readings, I made a custom LCD module driven by an ESP32C3 microcontroller. With the display in place, continue by mounting the AC inlet socket to the rear panel and connect the wiring to the input terminal block. Finally, mount the fan and close the case. With that, the build is finally complete. With the build complete, let's run a series of in-depth tests to find out how the power supply performs in real life, starting with a stress test. First, I mounted 4 temperature probes onto the critical power components to log their thermal profiles over time. A power meter was connected at the AC input to track the total energy consumption. For the load, I used an adjustable electrolysis tank tuned to maintain the maximum 1 kW power curve. The test was then run continuously for 1 hour. Exactly 1 hour later, the test concluded with the following results. The setup consumed a total of 1.111 kWh, averaging a sustained input of 1111 watts. Based on the input to output ratio, the calculated efficiency is 90%, which means the power supply dissipates 111 watts of power as heat. The thermal log shows the components reach thermal equilibrium quickly. The primary heatsink plateaued at 75 degrees Celsius, the main transformer reached 55 degrees Celsius, the secondary heatsink set at 69 degrees Celsius, and the output inductor held steady at 44 degrees Celsius. These temperatures showed that the cooling solution is adequate at keeping the components at safe temperatures. With the thermal profiling finished, it was time to dive into the efficiency and ripple characteristics of the supply. I evaluated the performance across the operating envelope, specifically at 50 volts with output currents ranging from 1 amp to 20 amps. To ensure I captured accurate output ripple measurements, I probed the PCB traces directly using a spring ground connection. I found that the forwarder 1 kW holds steady at approximately 89% efficiency for most loads above 25% capacity. At full load, the system hits 89.1% efficiency. This means the unit dissipates 122 watts of power as heat while drawing 7.25 amps from the mains with a power factor of 0.71. As expected, the efficiency dips slightly when I run the unit at lower loads. When I measured the output ripple, I noticed it tracked closely with the load. Under no-load conditions, the supply operates in pulses, which produce a single 40 mV peak-to-peak spike. With a 1 amp load, I recorded 33 mV peak-to-peak, which then scaled linearly until it hit a maximum of 94 mV peak-to-peak at full capacity. In this part, I characterized the power-on behavior by monitoring the output rise times. I found that under high load conditions, the SG3525 soft start function governs the curve, creating a smooth 1-second ramp up. At light or no-load conditions, however, I observed that the output voltage tracks significantly faster, with a voltage overshoot of several volts at lower set points. I evaluated the dynamic load performance by using a third electrode on a toggle switch. I tested transitions from no-load to 10 amps, as well as intermediate steps between 5 amps and 10 amps. During the no-load to 10 amps transitions, I measured a minor voltage drift of approximately 3%. In contrast, transitions between 5 amps and 10 amps demonstrated high stability, with no detectable voltage spike or overshoot. I also tested transitions between constant voltage and constant current modes by toggling between a 50 volts 5 amps constant voltage state and a 25 volts 10 amps constant current state. During constant voltage to constant current transitions, I observed that the current loop initiates a response in under 3 milliseconds, reaching full stabilization within 7 milliseconds. Conversely, constant current to constant voltage transitions occurred almost instantaneously, with the voltage loop settling in under 3 milliseconds. Finally, I analyzed the response to a sudden output short circuit. I found that the constant current loop handover occurs at approximately 1.5 milliseconds, with the system settling after 3 milliseconds. Under dead short conditions, I noted that the regulated current exhibits an oscillation of 10 amps peak-to-peak at a frequency of approximately 2.2 kHz. With the regulation test done, I focused on validating the switching performance by scoping key nodes under full load. On the primary side, I observed 24 volts peak-to-peak ripple at 100 Hz on the bulk capacitor, with voltage swings between 268 volts and 292 volts, while the DC blocking capacitor showed a ripple of 14.2 volts peak-to-peak. I then moved to examine the lower MOSFET's gate and drain to source voltages. The 9-volt drive signal clearly inhibited Miller effects. By zooming in, I captured precise switching speeds. At turn on, the gate to source voltage rose in 572 nanosecond, while the drain to source voltage fell in 184 nanosecond. And at turn off, the gate fell in 556 nanosecond, with the drain rising in 56 nanosecond. Next, I scoped the transformer's primary side, where I noted a slight 75% overshoot upon switch off that dissipated within 2 cycles. On the secondary side, I found that 64 volts RMS was required to maintain the 50 volt 20 amp output. The diode junction waveform showed a 114 volts overshoot, a 42% spike that also settled safely within 2 cycles. The in-depth testing wraps up our video today. As always, the resources are available as an open source project. If you find it useful, please consider supporting my work. Thank you for watching, and I will see you next time.